Thank you for your interest in my poster on the synthesis of silicon nanoparticles from hydrogensyl sesquioxane. While I was unfortunately ultimately unable to attend the conference in person, I have prepared a quick overview of this work as well as attached my contact info for any further questions. To start, silicon nanoparticles, or SiNPs, belong to a class of semiconductors known as quantum dots. As well, the high natural abundance, low toxicity, and biocompatibility of elemental silicon make them valuable and versatile materials. They are particularly important due to their size-dependent optical and electronic properties. For example, small particles less than about 10 nanometers in diameter are known for their photoluminescence and are excellent candidates for electronic displays, whereas larger silicon nanoparticles make for attractive optical metamaterials due in part to their interactions with visible light. Regardless of the application, however, it is crucial to be able to make these. An inexpensive and straightforward route for accessing nanoscale silicon particles involves the high temperature thermally induced disproportionation of hydrogensyl sesquioxane, or HSQ. HSQ being a polymeric silicon-rich oxide precursor with a unit formula of HSIO 3/2. Under these conditions, HSQ will undergo a stepwise decomposition to ultimately yield silane gas within a silica or SiO2 matrix. As the silane is trapped within the matrix, it can undergo further decomposition into elemental silicon and hydrogen, from which our silicon particles can evolve through a solid state Oswald ripening type mechanism. Previously, it was assumed that particle growth was continuous and unrestricted, with larger particles attained by processing at higher temperatures and for longer, with these particles able to become liberated from their silica matrix for further applications upon exposure to hydrofluoric acid or HF etching. However, this assumption is faulty, and instead there exists a discrete temperature region between approximately 1500 to 1600 degrees, in which the previously inert SiO2 matrix undergoes a solid-solid phase change to form the reactive crystalline or cristobalite phase of silica. This crystalline phase and any elemental silicon nanoparticles present within the composite then undergo a direct reaction to consume the SiNPs and leave behind only residual silica. The product of this reaction, volatile and gaseous SiO, or silicon monoxide, is then lost from the sample with the flow of argon gas down the furnace tube, but can be collected as the condensed orangey brown spongy solid on the furnace outlet valve. This new mechanism was established primarily through two experimental sequences. First, the exact parameters of this time temperature region were quantified by preparing a series of HSQ-derived composites with temperatures between 1400 to 1700 degrees, with dwell times ranging from 1 hour to 10 hours. Powder X-ray diffraction, or XRD, analysis of these composites revealed an inverse relationship between the amount of crystalline silicon, our silicon nanoparticles, and crystalline silica, the matrix. In other words, silicon loss is maximized with the highest degree of silica matrix crystallinity. Softening of the matrix at 1700 and unpredictable cooling at this point are then thought to account for the reemergence of trends above this anomalous region, but this is yet to be fully established. Further, X-ray photoelectron spectroscopy, or XPS data, is also provided to confirm the loss of elemental silicon zero under these conditions. Scanning electron microscopy, or SEM images, as well as energy dispersive X-ray EDX mapping of this spongy material that was found on the furnace outlet valve, as was mentioned in this mechanism, confirms it to be silicon monoxide, SiO. In an effort to better understand this reactivity, we attempted to replicate the behavior of the HSQ systems by grinding mixtures of both components in the form of silica and silicon powders. These mixed powder systems were then annealed in an effort to consume silicon similarly to what was seen in the HSQ parallel system. Worth noting here is that the silicon nanopowder source used in these experiments differed from the behavior of bulk silica in the HSQ system and in the phase diagram given below. And this nanopowder began crystallizing as low as 1400 degrees and producing the same reactivity. This was thought to therefore provide more confirmation that the matrix crystallinity is our missing puzzle piece to the SiO formation in HSQ. In this system, we were able to successfully copy the results observed in HSQ, as seen in our XRD data, with a significant consumption of crystalline silicon domains, as seen here. We also observed the formation of copious amounts of the same spongy SiO material as is seen in the HSQ system. Therefore, we now know that the accepted mechanism of silicon nanoparticle evolution from hydrogensyl sesquioxane is incomplete and not as straightforward as previously thought. We've collected a number of pieces of indirect evidence to support a solid state reaction between the silicon nanoparticles and the crystalline cristobalite SiO2 between 1500 to 1600 degrees, but the exact cause of this remains to be explored. Once this reactivity is better understood and more easily able to be controlled, we hope to find a way to mitigate silicon monoxide formation in HSQ and extend this particle synthesis to a wider variety of particle sizes.